Hello, everyone. My name is Munyakazi Natasha Alia, and this is our group. This is Group One, and I'm with Jonathan Chiribo. And our project is titled A Semantic Aware Data Warehouse for Crowdsourced Based Surveillance for Example. So, this research focuses on improving epidemiological surveillance in low resource settings such as Uganda, using semantic technologies, knowledge graphs, and neurosymbolic AI. So this work was developed under Department of Computer Science at Makerere University. Straight to slide two, and this talks about the introduction. So traditional health surveillance systems mainly rely on relational databases and OLTP systems. So these systems work well with structured they work well for structured hospital records, but they struggle with multimodal data such as images, unstructured text, and geospatial metadata coming from community reporters. So in Uganda, many communities now use smartphones, right? Creating opportunities for crowdsourced disease surveillance for conditions such as mpox, measles, and chickenpox. However, the challenge is ensuring data trust, provenance, and semantic consistency. So therefore, our project proposes a semantic aware data warehouse that combines knowledge graphs, ontology-driven reasoning, and AI-assisted ingestion to improve epidemiology. I've talked about the domain application. I've talked about the motivation, that is motivating us. So the traditional relation warehouses that I've talked about, that persistent, the data, I think some of our the deployment constraints that are already there is that the environments we are in, we're able to get inconsistent data. But since now Ugandans use smartphones, we searched through the related work and we reviewed several existing approaches in epidemiological surveillance. These are some of them. I won't talk about all of them, but some of the systems depended heavily on cloud infrastructure and introduced computational latency. Some lacked semantic reasoning capabilities. Other systems based on relational warehouse struggled to manage text relations effectively. So from this review, we identified the research gap as the lack of systems that combine multimodal AI, semantic reasoning, and offline fast deployment in low resource environments. So basically, what are our problem statements? So the computational problem was structured using an 8-layer locator framework. At layer 0, the main task is epidemiological evidence generation. So I'll explain this. The system then uses weak supervision, and human validation to support semantic retrieval and disease classification. The data itself is multimodal, meaning it includes images, text, and geospatial metadata. So since the environment is low resource, as I've mentioned earlier, the system must also support offline, fast mobile edge development, and privacy preserving processing. So that architecture then integrates neurosymbolic reasoning by combining deep learning with knowledge graph reasoning. Basically, that is it, by make it short. What are some of our research questions? So the first research question investigates how semantic warehousing can improve trust in crowdsourced epidemiological data. I talked about how the works before had the trust issue, the provenance issue. So how can we improve the trust in the data that we are getting? The second focuses on improving consistency between dermatological images and clinical metadata using neurosymbolic AI. We also investigate how offline fast ingestion pipelines can operate under low resource. Finally, we examine how semantic retrieval improves explainability and evidence traceability. So the project objectives therefore include developing a semantic aware data warehouse. That's where we get our objectives from so that we can answer these questions. And then we implement LLM assisted ingestion. We construct a neurosymbolic framework and evaluate out of distribution. Then I'll go to our research contributions. What were we able to do? So the project makes four major contributions. One, it improves multimodal benchmark data set for exam them surveillance in Uganda. It introduces, pardon me, an ontology-driven knowledge graph for semantic epidemiological reasoning. Then thirdly, it processes an offline fast semantic ingestion architecture suitable for real deployment. I'll be showing it to you later on. And then it integrates, of course, you have to have a model that's going to detect, the images that would have provided it. So it integrates CNN-based perception with graph reasoning using a neurosymbolic framework. Then the methodology and system architecture, I think I've talked about it, like the 8-layer locator framework. But the methodology begins with decentralized mobile edge ingestion. The community reporters submit images and metadata using the mobile devices. Then each artifact is assigned a cryptographic hash to preserve the provenance and trust. Remember, we said we also want to try and improve trust. So we have to bring in these cryptographic hashes. Then a large language model performs schema-constrained extraction of symptoms, the lesion prescriptions, descriptions, temporal projection, and geographic metadata. So these extracted entities are then validated against standard ontologies such as the SNOMED, DT, and ICD-11 to reduce semantic inconsistencies. Finally, the validated entities are inserted into a semantic knowledge graph which supports reasoning and semantic retrieval. Yes, basically that is it. This is some of our data set description and the EDA. So the data set we got was from Cabo, and it consisted 1,248 multimodal instances, including mpox, measles, and chickenpox samples. So the knowledge graph contains over 1,000 artifact nodes and more than 6,000 semantic relationships. So during EDA, we observed class imbalances and graph sparsity. So we know this means that some diseases had more samples than the others, and some regions had fewer semantic connections. So we tried doing the data augmentation so that we can predict the flips, the rotations. Yeah. So these findings influenced our preprocessing and evaluation strategies. Then the AI models and mathematical familiarization. So the architecture combines neural perception with symbolic reasoning. First, I'll talk about the CNN, the CNN encoder. It extracts visual embeddings from the dermatological images. Then these embeddings are then passed into a message passing neural network operating on the knowledge graph. The graph reasoning stage models relationships between the symptoms, the locations, and the disease classes because they must be consistent. They must be matching with each other. And remember, it is displayed after on. We shall show you the system. So this neurosymbolic integration improves explainability and diagnostic consistency compared to the standalone CNN approaches. Yes. That's basically our formulas. That's what they're trying to show. Then I'll go to the evaluation, the benchmarking and governance. So the system was evaluated using out of distribution robustness testing. So instead of random train test splitting, we used spatial holdout evaluation. The model was trained on one geographic region and tested on another to better simulate real world deployment. So this proposed neurosymbolic model achieved higher accuracy, precision, and F1 score compared to the CNN baseline. The retrieval latency was also reduced significantly when using semantic graph querying instead of traditional SQL joins. So in terms of governance and privacy, the system applies partial k-anonymity and differential privacy to protect sensitive community data. Then I'll talk about the business intelligence. This is in our work, business intelligence is treated as a semantic evidence generalization layer, and rather than just a simple visualization. So when a health official investigates an outbreak alert, when a health official investigates an outbreak alert, the system retrieves the exact semantic subgraph and provenance information responsible for the prediction. So this improves explainability, traceability, and trust in AI-assisted epidemiological directions. For you. So it's showing the temporal transmission trends of the different districts over a period of time. Then when you go here, you can capture an image. You can either take a picture or you can upload. So let me say a clinician is the one taking this image. They upload it there. They can give the symptoms of what is happening, the region they are in, and then that's it. And then it will give you that it has already stored. And after it's stored, you can easily download it from there, from the knowledge graph view. Ops deployment and edge orchestration. So since many rural regions experience unstable internet connectivity, the system uses an offline fast deployment strategy. So the local databases, they temporarily cache reports on mobile device until connectivity becomes available. So synchronization is then used to update the central semantic warehouse efficiently. So in addition, a lightweight quantized model is deployed to reduce memory and computational requirements on mobile devices. That's it. Then I'll go to the limitations. So despite the advantages of this architecture, several limitations remain, like a semantic drift, how when localized clinical terms are interpreted incorrectly by the ontology. Then there could also be graph sparsity, which can reduce reasoning performance in newly deployed regions with limited historical data. Then additionally, applying differential privacy introduces a trade-off between privacy protection and extraction accuracy. Yeah. Then this slide basically, as I'm concluding, the project demonstrates that semantic aware knowledge graph architectures can improve crowdsourced epidemiological surveillance in low-resource environments. So by integrating neurosymbolic AI, semantic ingestion, and offline fast deployment, the system provides more explainable and trustworthy epidemiological intelligence. Future work will focus on a tiny ML deployment, localized language models for processing, and federated learning for privacy preserving multi-district training. Then these are some of the references. These are the academic references and datasets that informed the research and system design. So finally, we would like to thank our lecturer, the School of Computing and Informatics Technology, and all contributors who supported the project. Thank you for listening.